So in this example of a approximately equal function that we defined in the form of an operator, we used a function called abs, the absolute value. And this function was, I just pulled it out of the air. It's because it's one of the standard functions that's already predefined for us in something called the prelude. But I think it's instructive to see how we might define this function ourselves. And the first and most obvious way, and the way that I will discourage you from using, because it will hamper your Haskell programming later. But the first and most obvious way to do it is to use a conditional expression. So we could have defined the absolute value of some number n in terms of a conditional. If n is less than 0, then we want to negate n, and there is a function called negate that does that. But actually we can actually even just use the minus sign, so we don't have to write the negate function, but sometimes it's clearer to do so. So we can write minus n to mean the negation of n, else it's just n. So that would be one way of defining it. Now, of course, this is already predefined, and so if we would define it again, whenever we use abs here, we'll get a compiler issue, because it will basically say, well, which abs did you mean? Did you mean the one in the prelude, or did you mean this one that I've just defined? So we will, if we want to actually redefine something that's already defined to illustrate how it's defined, I'll typically rename it. Now, it can be defined this way. Let me just comment that out. But I want to show you a different way, which is going to be a bit more powerful and flexible. And that is to give definitions by using what are called guards. So a definition by guards is a definition that is defined by cases. And the definition of the absolute value of n in the case when n is less than 0 is equal to minus n. And the definition of the absolute value of n in the case when n is greater than equal to 0, it will just be the value that we started with, n. So here's an example of a definition which uses guards, and it's a way of giving definitions by cases. So when Haskell has these forms of definitions, it will always start with the first line and say, if it wants to calculate the value of abs of some value, it will first see whether this guard is satisfied. Is this guard true? And then we know the answer is this. Otherwise, it moves on to the next equation. Now, the first thing to note is that when we have multiple guards with the same left-hand side, in this case, abs prime of n, we can remove this and treat them as a single equation defined by two cases. So this is a single definition of abs with two possible cases. So that's the first simplification that I can make to this definition. Okay, but we're not finished there. We can simplify this a bit further. So these are all valid, but this is useful to see that in fact that we can write it in more than one way. If this equation doesn't match, in other words, if we apply it to a value n which is not less than 0, then this will always be true. So this test is redundant, in fact. So we can replace this test with true. This is the guard that will always be true, because we know that we will always get the value true if this one is not true. Now, stylistically, this is some people actually would write the definition in this way, but I think in all the textbooks you will see it won't be written this way. It will be written using another expression, which makes it more readable, I think, which is otherwise. So we typically will line our equations up. So this will be the typical way that you would see this defined in a textbook. The absolute value of n, if n is less than 0, is equal to minus n. Otherwise, it's equal to n. Now, you may at this point wonder whether otherwise is a Haskell keyword, and it turns out that it's not a Haskell keyword. In fact, we can ask the interpreter to give us information about otherwise, and as we can do with all constants and functions, it will tell us that otherwise is this double colon here is otherwise has type bool, and it's defined as part of the basic Haskell infrastructure that is imported by the prelude. So if this is a value of type bool, then we can use it just like any other value. We can type it at the interpreter to find out what the value is. What is the value of otherwise? It is true. So something you'll note about values in the data of Boolean type, bool, they start with a capital letter. So the values of bool will be true and false, and those true and false will start with a capital letter. So all Boolean valued expressions will evaluate to either true or false, including, for example, this function prop exchange. Okay, so this is just introducing how you can ask the interpreter about things that it knows about, and it will tell you what their type is and where they live, and perhaps a bit more information. Okay, so we've seen an example of a definition by cases, and we'll see this is a very useful and powerful mechanism, and that can be combined with other ways of defining functions, and we'll see lots of examples of that. So don't reach for your familiar if then else, because if then else is a bit more limited. It can define it by a single pair of cases when something is true and when it's not true. This can be defined with any number of rows according to the needs that you have. So it doesn't have to be one guard and one otherwise. It can be any number of guards, and it would only make sense to use otherwise on the very last case as a catch-all.